Good morning, everyone. I appreciate your attendance here today. I'm excited to talk to you about research that I'm very passionate about. I've spent the best part of 4 years working on. We're all aware of the success stories of machine learning and the applications that that has generated in many fields. There's this sense of objectivity in being data-driven and letting the data speak for itself that I think is very appealing. So it's only natural to ask how tools and ideas from machine learning can help us meet the scientific task at hand. And for me, that scientific task is discrete choice analysis, which, as many of you know, is not purely data-driven, but involves a lot of theory. So the goal of my thesis is to try and realize some synergies between the data-driven and the theory-based approaches in the context of discrete choice analysis. And to be able to realize this synergy, we need to understand the role of data and theory. So my presentation has two parts. In the first part, I very quickly recap the setting in which discrete choice models are applied, the type of problems that we're interested in, and through this understanding, reaffirm the role of theory in model building, but at the same time, identify some desirable data-driven capabilities that we want to bring over to advance the state of the art in discrete choice, basically to empower us to do what we want to do better. And in the second part, I describe a framework to which this synergy can be realized. And I talk about some applications. So the goal of discrete choice analysis is to predict behavior in counterfactual settings. So we want to evaluate the impact of different policies, such as the effect of a fuel surcharge, for example, on congestion. We're also interested in extracting an individual's willingness to pay, calculate things like societal welfare, among many other use cases. In essence, we want to understand what will happen if. And to do this, we need to build a causal model. I want my model to tell me, for example, if I reduce the travel times by X minutes, bus ridership will increase by Y%. So it is clear that we need data to do analysis, but why do we need theory? Well, data is not a monolithic object. There's different kinds of data sources. The first two are some kinds of experiments. The first one is a real experiment. I effect a change in a system and I record its outcome, but this type of experiment is difficult to do in a setting of interest. The second one is a simulated setting where you can ask people to state choices they would make under various scenarios. So I can show a proposed scenario where the transit travel times are reduced, and I study how people's transit choices change. Now, obviously, people say they will do one thing, but they could actually do another thing. So there's a validity question there. So the third type of data is by far the most common, which is the observational data, where we observe variability in travel times, for example, experienced by different users, and then look at how this affects their choices. So notice how here we're trying to answer a proactive question, which is the what if analysis question, using passive observations. And so there's a mismatch between the application and the data that we typically have. And so any predictor based only on this type of like passive data is bound to reflect this mismatch. And that's the limitation here of going fully data-driven. Because it could be, for example, that people don't take bus because transit travel time is low. It could be that their transit travel time is low because they prefer to take the bus and they locate closer to have better access to transit. So we would reach the wrong conclusions if we pretended that the estimated effective travel time from this type of observational data is causal when it's not. And so the standard in discrete choice and in econometrics more generally is to lean on a theoretical framework that will allow us to motivate assumptions and other strategies that will sometimes allow us to sort of deal with this kind of confounding. For example, the hybrid choice model is type of a structural equation model that will allow us to explicitly model these attitudes on transit and address at least some of the bias. So the bottom line is we need to work within a theoretical framework to address causality. That's the first point I want to make. More broadly, there are additional capabilities that are essential for discrete choice analysis. We just talked about the first one, which is an intervention, where we are interested in a what-if analysis or type of a proactive question. The second is extrapolation. So regardless of the data source, the range of observation is typically limited. And the shape of a data-driven function outside that range can be anything. So we need theory in terms of a global shape restrictions to tell us how to extrapolate. And the second aspect of extrapolation is obviously forecasting. So for example, if you know, or if you assume that individuals are, for example, like utility maximizing, we can say that, well, in the future, they will continue to maximize utility. And so we can use behavior observed today to forecast behavior in the future. This kind of extrapolation, you need some kind of a theoretical basis for. And then the third item here on the list is interpretation. I know this term is a little bit overloaded, but in this setting, a model is interpretable if its predictions make sense. And it makes sense, meaning it can be justified or explained using theory, because when we do this type of analysis, we're doing what's called a confirmatory analysis, meaning we already have in mind some notion of why and how an effective interest comes about. And when output is contrary to expectations, you really look at your model assumptions, and any unexpected results are taken as suggestive until substantiated. So this understanding of interpretability has nothing to do with, if you use a linear form or not, because a linear regression could be uninterpretable in the context of analysis if it produces results counter to expectation. For example, if you don't address bias. So in summary, we need theory in addition to data to do analysis. Now, while we can't refute the logic of the theory-based approach that we need to combine data with theory to reach sensible conclusions, the credibility of some assumptions made under this theory paradigm is not necessarily a foregone conclusion, because there's often a tendency to invoke assumptions far stronger than can be persuasively defended. So I think that's an area where data-driven ideas can be brought in to help. Not all assumptions are created equal. Some are rooted in theory, such as utility maximization or monotonicity, but then others are made out of convenience, such as linear effects. So the benefit with simple specifications is that they're easy to diagnose. You can check the coefficients, the ratios of parameters, but this often comes at the expense of predictive accuracy and the risk of model misspecification. So the standard practice in model building in discrete choice is to start simple and add complexity incrementally, but there isn't really a systematic way of adding complexity. It involves a lot of guesswork. And in theory, you should pick one or two models out of principle and estimate on the full data set. But what ends up happening is you estimate much more models in the background and cherry pick what you want to present. So the model selection process is not documented and cannot be replicated by other researchers. So this model selection process also does not take into account the sort of inherent uncertainty in model selection, and so the confidence intervals that you report may not necessarily be valid. So Mansky famously calls this incredible certitude or certainty without credibility. And the fact that the model's policy implications may be predicated on an unsystematic process, that poses a serious credibility concern. So for example, welfare measures may be biased if you pick the wrong nested tree in a nested logit model. The willingness to pay distribution may be biased if you don't account for the right covariances in the logit mixture model. So clearly something can be improved here. And this is in contrast to ideas from machine learning, where the specification is data-driven, the model development is more systematic, and the process is fully documented. And so we would like to bring some of these desirable capabilities to discrete choice analysis. We would like to address the incredible certitude, so to speak, of these models by placing aspects of model specification under a more rigorous and systematic framework. But at the same time, we need to do it carefully, because we don't want to lose the essential capabilities of analysis that are described earlier. We don't want to, as people say, we don't want to rob Peter to pay Paul. We don't want to do something at the expense of the other, and we don't have to, because the two paradigms are complementary, really. So the idea of this thesis is to start with a theory-based framework, and then to bring in these capabilities as needed. Which brings us to the second part of this presentation, where I describe the framework to do just that. I first describe an overview of the framework, how it relates to others in the literature. Then I talk about operationalizing this framework, and finally introduce some applications. So to bring in data-driven capabilities, we start with a theory-based model, which already has some strong methodological grounding. We don't throw that away. Let's take what we have and build on it. This way, the machinery of causal inference that has been developed over many years remains applicable to deal with confounding, which is often present. We then identify areas of model specification where data-driven flexibility is needed. Let's take a look at the most tenuous assumption about a discrete choice model that we feel will affect policy decisions, and let's decide to add flexibility there. This could be the functional form of the utility, where you want to add some nonlinearities, or it could be the structure or distribution of the stochastic error terms. In step 3, we find constraints to impose. So we basically formalize our expectations of the model in the form of mathematical constraints and insist that the model be consistent with these expectations. This consistency with theory is basically a guarantee, or allows us to have a certificate of trust that the model will not produce counterintuitive results. Next, we develop an algorithm to basically find an optimal specification. It's akin to conducting a data-driven algorithmic search of theory-consistent specifications. And this will require some non-standard tailored solution methods. And a lot of the work in this thesis is in developing such solution methods for specific problems. So the optimization problem that we have is to choose a specification and its associated parameters that maximize likelihood while avoiding overfitting. And here we've got ideas from validation and regularization from machine learning to find the optimal complexity penalty. All this subject to the theory constraints that we identified. Now, finally, it's important that we validate these constraints through the data. Some constraints have testable implications, and clearly the constraints we impose are not arbitrary, and you would typically only impose constraints that you are prepared to defend. The purpose of adding these constraints, of course, is as I said, is to guarantee consistency with theory. So they make the model more trustworthy, but not necessarily more credible, because like credibility at the end of the day comes from the real world system, not my expectations of it or anyone's expectations of it. And so data which captures a cross-section of that real world system can be used to validate these constraints, or at least not invalidate the imposed constraints. So we need to run some kind of hypothesis test to maintain credibility. And it can also serve, as we'll see, as an important diagnostic tool to see that we're not masking any underlying issue with the model. So the scope of my thesis is to operationalize this framework. Could be a nice framework on paper to talk about, but it needs to be operationalized. So meaning I'm going to look at commonly used discrete choice models, identify some of the areas where flexibility is needed, identify what constraints should be imposed, and then propose practical solution algorithms that work and are statistically consistent. And I demonstrate consistency using Monte Carlo data. And then once consistency is established, I estimate the model on real data set. So there's sort of two, how does this sit in the discrete choice literature? There's a lot of research that wants to bring data-driven flexibility to discrete choice analysis. I divide the literature in two. The first stream starts with data-driven models, and the second starts with theory-based models. So in the stream that starts with data-driven models, use discrete choice analysis as a classification problem instead of a causal inference problem. So this start with classifiers like a neural net or a random forest. And the level of sophistication varies from completely replacing the model with a machine learning classifier to being a little bit more thoughtful about augmenting the specification. We notice that there is gains in predictive accuracy, but the price to pay is typically consistency with theory. When you try and look at the output at a more granular level, you sort of see counterintuitive output. And I identify here three challenges why I think this approach is at a severe disadvantage compared to starting with a theory-based. Number one, we don't have a clear framework to deal with confounding. The econometric framework is not necessarily applicable in a neural net, for example. It is not clear if the classifiers are consistent with any behavioral framework. So consistency with utility maximization, of course, is important because it provides us a link to microeconomics, and it provides us for a basis to estimate willingness to pay as a marginal rate of substitution between price and the other attributes of alternatives. But some of the classifiers capture substitution effects, for example, through the observed component, which generally breaches the regularity and makes the model inconsistent with utility maximization. So there's other two that I identify here: difficulties in troubleshooting. When you notice something is wrong, it's not really quite clear what to do. With theory-based approach, you can motivate different assumptions, different moment condition. And then finally, lack of trust that arises through over parameterization. So over parameterization in machine learning is sometimes viewed as desirable because you can use a local descent method and then it tends to converge to global optima. But over parameterization can be a double-sided sword because it creates an equivalence class of loss minimizing solutions, and the specific solution obtained at convergence could be subject to arbitrary initialization settings, but each of these solutions may have different implications when you look at the output at a more granular level, which is what we do with policy analysis applications. So the key conclusion here is that you can't wait for regularity with theory to just happen by luck. We need a framework for it, and we need to impose consistency with theory as a constraint. The second stream starts with theory-based models, and approaches under this category are, say, few and far between compared to the first approach. The main idea is to enhance the flexibility of the theory-based model. Sometimes classifiers are used to assist with model specification. For example, you can use it to identify some kind of nonlinear effect, more as an exploratory tool to study the data, and then take some insights from that into your model. But they're not used directly or in conjunction with the theory-based discrete choice model. So this framework falls under this approach and is distinguished by constraints on the introduced flexibility, followed by hypothesis tests to validate those constraints. And the applications are also different in terms of this specific applications that we show later. Okay, so what's the big picture? There's some recent successes in trying to realize synergies beyond the field of discrete choice models. Recently, a win-win combination has involved combining or exploiting the fact machine learning methods work well with high-dimensional data. So you can try and leverage this predictive power while working within the econometric framework. That's the first line of research that I have here. And there's a newly emerging field of scientific machine learning where among the different ideas that have been proposed is to try and modify the objective of machine learning models by adding a loss function that measures violations of known physics. So you kind of tether the output to be consistent with physical constraints. So that's the overview of the framework. Let's now talk about the operationalization of the framework before looking at some applications. So here's a somewhat formal presentation of the framework that I showed earlier. Remember, we start with a theory-based discrete choice model. We identify where flexibility in that choice model may be desirable. These two decisions determine this set curly M. And the goal here is to maximize the likelihood, both as a function of the specification decisions and the model parameters. And we want to do this while avoiding overfitting, so we don't end up with the maximal or the most complicated specification. So we have a penalty term there in the objective. And the theory constraints are embedded in these sets SM, which restrict the parameters in such a way that the model agrees or that the model output agrees with theory. So I'll give an example in a moment, but at a high level, from a conceptual point of view, the inferential action now takes place at a wider scale because we're dealing with models and parameters instead of just parameters. And the implication of that is that from a computational point of view, this will involve more complex structures, and there are many specificities that require tailor-made solutions. So as a quick example, we'll look here at the nested closures model. The tree structure determines the dependence among the stochastic terms and the utility equations. Of the alternatives here, we have 5 alternatives. So the structure tells us which terms are correlated, and the scale parameters theta here determined by what amount the scales are correlated. So if you want the data to decide which tree best describes the choice behavior, we define the set curly M to include all nested logic tree specifications. So this is an example of one such tree in the set curly M. And then we can define constraints to basically guarantee that these scale parameters are consistent, or that the model will be consistent with utility maximization, which is basically that the scales are increasing with depth. So to operationalize this framework, we actually need to do some work. So the presentation that you've seen is sort of, let's say, like a stylistic presentation. So if the models are nested, let's say if M is the index of the degree of a polynomial, for example, you can start simple and then add complexity incrementally until out of sample fit deteriorates. But often the models are not nested. And in that case, one way to go about solving the problem is to reformulate it using integer variables and then to use some kind of approximation technique. So for example, for the nested logit problem, it is actually a non-nested model because there are many trees that are not special cases of one another. So you could think about introducing integer variables that represent whether there's an edge between one node and another, and then you formulate it using this small subset of integer variables, and then you use techniques from optimization to sort of try and approximate a solution to the problem. Okay, so quickly on the estimator properties, if we think of the model indices as integer variables, the estimator is a constrained, regularized, mixed integer optimization problem. And there's some work on discrete parameter space, maximum likelihood properties. There's some work that I cite here, and these results may serve as theoretical support for some desirable properties for the proposed estimator, but I don't provide any generic proofs of such properties in my thesis. Instead, I demonstrate consistency empirically through Monte Carlo. The main practical implication is, though, that the standard error is accounting for the precision with which we estimate the model, or with which we select the model, can only be obtained through resampling techniques such as bootstrapping, which can be computationally intensive. So this and the challenge of the optimization problem itself makes us believe that a Bayesian approach has a potential to place the proposed estimator on a stronger footing in terms of the statistical properties, while avoiding many of the optimization difficulties. So instead of viewing M and theta as decision variables to be found by maximizing likelihood, we instead treat them as random variables with some prior distribution. And the prior over M can be chosen to favor simpler models. The prior over theta can be made to reflect theory constraints. And the goal now is to sample from the joint density of model and parameters conditional on the data. And because there is no closed form for this posterior generally, we rely on Monte Carlo methods where we now have to adjust for the varying dimension, because the parameter space varies from model to model, so we need to make some minor adjustments. So finally, hypothesis tests and then application. So we impose constraints during a specification search where the constraints have the support of some scientific theory, and the goal now is to validate these constraints. So there's the test is the constrained model against the unconstrained model, but you could test this constraint at 3 levels. The first one is the parameter level for the same model, and the second one at both the parameter and model levels, taking into account the possible dependence of the optimal model on the constraint set and whether you impose constraints or not. And then finally, at the most general level, you can include uncertainty in model selection as part of the test, because there is a precision with which we select the model, and that should ideally be also incorporated inside the test. Now, the first and third one, for example, are nested hypothesis tests. And with nested hypothesis test, likelihood ratio test comes to mind. But we typically can't lean on nice asymptotic theory that will give us the distribution of the statistic under the null, because we're imposing all kinds of constraints, and the regularity conditions aren't always met. So we have to resort to bootstrapping. But then for the classical case, for the Bayesian case, there are different ideas. One is to compute the base factor. And then the second one is to view testing as a 2-component mixture estimation, where you define an all-encompassing model as a convex combination of a theory consistent and a non-theory consistent model. And then you sample the weights, and then by looking at those weights, you can determine which one the data favors, which component the data favors. Okay, so finally, I need to make a short comment about what to do when we reject constraints. So the rejection occurs in the context within which the constraints are imposed, and a rejection indicates some kind of shortcoming, a possible shortcoming that the null is advocating. One possible reason is indigeneity. For example, we could impose the constraint that demand is a monotonically decreasing function of price, but in my model, based on the data that I have and the identification assumptions that I impose, I don't have the effective price identified. The monotonicity constraint may sort of apply to the partial effect of price, or say like the partial derivative of price. But what I have identified in my data is the total effective price, which is not necessarily monotonic. So I need to revisit my identification assumptions and maybe use some kind of an instrumental variable to identify the partial effective price, and then reimpose this constraint. So, but the main thing is now that since I'm working within the theory-based framework, I know what to do next, and I can motivate different strategies or maybe change the model class as appropriate. So finally, we move to some applications. So I divide the application by the type of methodology. The first one is the classical. The second one is Bayesian. So we're in the discrete choice context, and with this random utility maximization framework, the utility that an agent associates with some alternative has a systematic and a random component. So the systematic utilities are labeled here BJN. This is the systematic utility of choice J to individual N. Typically, it's assumed to be linear, meaning it only considers the linear effects of the different attributes and the different characteristics sometimes involves some interactions and some handcrafted transformations. But what we would like to do here is we'd like to have a flexible specifications for the systematic utility. So we want to introduce flexibility, but at the same time, we want to temper this flexibility with constraints. And those constraints typically take the form of sign constraints on the partial derivative, and sometime on also higher order derivatives, such as the ones mentioned here. So for example, we may want the probability of travel mode K to be decreasing as a function of its travel time, etc. Okay, so the methodology I used to enforce these sign constraints is to specify these systematic utilities or their derivatives as sum of squared polynomials. So why polynomials and why the special class of polynomials? Well, polynomials are generally attractive from a computational point of view because they're linear parameters. They're generally found to be flexible approximations of well-behaved functions. More importantly, when you take the derivative of a polynomial, you also end up with a polynomial. So you can use the same method that you use to constrain the sign of a polynomial to also constrain its higher order derivative. So it keeps things nice and tractable. But why SOS polynomials? Well, generally speaking, verifying that a polynomial is non-negative is a hard problem. But if a polynomial has an SAS factorization, so basically an SAS factorization is basically that you can write the polynomial as a sum of squared of polynomial. So if you can do this, then clearly the polynomial is non-negative. So its non-negativity can be verified simply by virtue of this representation. And it turns out that this verification can be easily done. This famous result from Perillo here. But then the question is, what do we lose? In the univariate case, you don't lose anything. So SAS factorization is also a necessary condition in addition to being a sufficient condition. And in the multivariate case, there is a result that says that any non-negative polynomial can be infinitesimally perturbed to make it SOS. But the caveat being is that the perturbed SAS will have to have a higher degree. So that's the price to pay here. Okay, so this is the framework, for example, if you want to impose a sign constraint on the systematic utility, we specify the systematic utility as a polynomial of degree d. You enforce a sign constraint on the derivative or on any of the higher order derivatives by, first of all, computing the derivative, which is a polynomial, and then constraining the coefficients to enable an SAS factorization, which can be achieved through a system of linear equations and some other auxiliary constraints. You then reformulate the problem as a conic optimization problem. You then add these constraints that we derive, and then give it to a solver. And then you would select D through validation. So let me give a quick example. So here is an example on an empirical data set that is used in transportation. The choices between Swiss Metro train and car. We want to fit a flexible specification for these for the systematic utility equation. The constraints that we have is the derivative with respect to time and cost are negative. We vary the degree, look at the validation for the constrained and unconstrained. We select an unconstrained and we select a constrained polynomial, and we see that the validation fit, the out of sample fit, is very, very close. So we're not losing much by imposing these sign constraints. See here this 403, 404. This is how the two specifications look. You see that the constrained one looks as expected, decreasing with respect to time, decreasing with respect to cost. The unconstrained behaves erratically. This is an example of using the constrained and unconstrained polynomial for forecasting. So here the thick line is the unconstrained, the dashed line is the constrained. And you see that even though we're still within the vicinity of observed data, so this is the spread, the joint spread of travel time and travel cost, the unconstrained still behaves quite unexpectedly. So we'd expect all these functions to be monotonic. Finally, we'd like to validate the imposed theory constraint, and we bootstrap the likelihood ratio, test statistic, and fail to reject the null hypothesis. Right, so moving on to another application, moving from the systematic component to the stochastic component. for the logit mixture models, which calls for randomly distributed parameters beta. And with this decision comes the question of which covariances in this matrix omega to estimate and which to fix to zero. The data may not have enough heterogeneity to justify a model with all distributed parameters, or having all covariances being non-zero. But at the same time, the distribution of things like values of time may be affected by which covariances you estimate or not. So we'd like to have a systematic methodology to decide which covariances to estimate and which covariances not to estimate. And the constraints here are that the blocks are, or that the matrix is block diagonal, because the story is that the reason we have these covariances is that because there are some missing variables or some missing factors that then cause these parameters to be distributed. So we can do the same thing, have an algorithm for a fixed level of complexity, or for a fixed measure of complexity, will give us a specification that meets the constraints, and then we vary this level of complexity in a systematic way. This is again the idea for machine learning that I've shown for the polynomial, and now I'm showing here. You then vary this level of complexity in a systematic way, and then you determine it based on out-of-sample validation. So here's again an example for the Swiss Metro. You vary P here is the number of blocks. When P equals 1, it's just a full matrix. It's the most generic specification. P equals to 6. 6 here is the number of distributed parameters. This is the diagonal specification. The optimal one here is this one shown here, P equals to 3. And this is the result of the optimization with P equals to 3. Basically saying that you should have one block with all these distributed, and then you should have 2 blocks where you don't estimate the covariances between blocks. Okay, so again, you could estimate, you could run a hypothesis test to sort of justify the imposition of the constraints that this restricted model is a justifiable model. So you get some kind of credibility. So finally, talk about the nested logit. So the nested logit model is obviously much more restricted than the logit mixture model that I've shown here, but it is still relevant because it's still very commonly used, and it has a closed form choice probability. So people still use it despite there being other more general alternatives. So the question for us is to decide which nesting structure best describes the behavior, the choice behavior of the population under study. People typically select 1 or 2 nesting structures based on what they think could be the right structure. But we'd like to, again, put this on a more rigorous footing. The constraints are that the scale parameters are increasing with nesting level so that the output is consistent with utility maximization. So there is an approach through an approximation technique. The limitation of that approach is that the standard errors have to be obtained through bootstrapping, and it's not entirely scalable. So the alternative is to use a Bayesian approach. And with this Bayesian approach, you're viewing the tree and parameters as random variables. You define a prior that favors less complicated tree by penalizing the average degree of the tree. You then have an informative prior over the scales, so that the scales have to be decreasing as you go down a tree. And then you synthesize or you construct a Markov chain with certain updates, such that the equilibrium distribution of that Markov chain is the posterior distribution. So there's a lot of details. This is the kind of updates that we have. This is an example for the nested logit tree with 3 alternatives. So you can jump between different trees to basically add a nest, remove a nest, or you can stay with the same tree and update, let's say, the scale parameters or the parameters in the utility equation. So finally, the last example I have here today is an example on the Massachusetts travel survey data. This is a choice between 6 travel alternatives. This is how the posterior looks like. This is the trees in the posterior, and you see there isn't really a clear winning tree in the posterior. And then we can use now that posterior to predict the impact of a policy analysis. So I started by saying we would like to do analysis. We'd like to see what the impact is of a what-if scenario. And then I said that sometimes when people make assumptions these assumptions are not credible. So here, for example, someone could start and say, well, I believe that this nested logic tree is the true tree, and then proceed to make analysis or do predictions based on that tree. But the credibility of that analysis is sort of not very clear, because that tree may or may not be the true tree. Whereas here, we're really, say, like integrating over, or we're optimizing over all nesting tree specifications, so that the analysis is much more credible, because it is not predicated on the tree being correct. We're just sampling from all like plausible trees, and the implication of this is that there is some uncertainty. There is obviously more uncertainty when we're predicting the impact of a policy. Okay, so in summary, the data-driven and theory-based approach are complementary. Going data-driven does not mean that that you have to obey a one-size-fits-all loss minimization approach and ignore everything in theory. And the primacy of theory is not at all inconsistent with giving data a measured role in model building. In fact, economic theory rarely dictates specific functional forms. It instead gives some high-level constraints, such as like monotonicity, homogeneity, etc. So there is indeed a huge opportunity for data to determine specification aspects under the guidance of theory. And with computation advances, I think we have a major opportunity for theory-based models to shed old computation constraints and better meet the demands of the analysis. So in summary, we have a framework for realizing synergies between the data-driven and theory-based approaches. The idea is to optimize or integrate away any arbitrariness that we think affects our policy implications. Both data and theory play an integral role. Theory provides the trustworthiness, make sure the output is not counterintuitive, and then data provides reality checks through the hypothesis test. And we also had some concrete examples. To rush through many of them, there are a lot of details in the paper. But thank you for your attention. I'm happy to take your questions.